Okay. Okay. Thank you very much, Arina, for the invitation. I'm very glad to be here with you. Okay. So today I'm going to talk about some connection between number theory and geometric knot theory. For doing this connection, we're going to use polytopes and sphere packings. So these works were done in collaboration with Jorge Ramírez Alfonsín from the University of Montpellier. So in this talk, there will be 5 parts. At the beginning, I'm going to introduce the problems and the motivation in geometric knot theory. Then we're going to talk about some geometric classic object, which is called a Polonian packing of circles. Then we're going to introduce the polytopes here and try to generalize this classic object. We're going to continue with the part of connection with number theory, which is given by an old theorem that is called the Descartes theorem. And finally, we're going to close the loop by connecting this Apollonian packing construction with knots. So please, if you have any question, you can interrupt me in any moment. So let's start with the part of geometric knot theory. So a knot is just a closed simple curve in the sphere, in 3 sphere, which is equivalent to the R3 compactified. We add infinity. So here we have a bunch of classic knots. A link is just a disjoint collection of knots. And we're going to classify these knots on links. Normally, they are written with a number, which is the crossing number, which is the minimum number of crossing that we can obtain in any projection. And we are going to look at some specific representation of knots, which are called necklace representation. Necklace representation of a knot of a link is just a sphere packing, which contains a polygonal representation of L inside the sphere packing, like that. So this kind of representation, necklace representation, has been used in hyperbolic geometry, for example, for compute the hyperbolic volume of 3 manifolds. Is a recent work of which use this kind of objects. Also, outside mathematics in molecular biology, this kind of a structure has been used for modeling molecular machines. And also, they are also useful for defining the formation of knots. Imagine that we have a knot or a link in the space, and we want to deform it continuously. And we want to apply a deformation that preserves self-avoidance and topology. For doing this, we can use a conformal deformation to this kind of a sphere package which contains knot, and the sphere packing are going to protect the topological structure of the knot or the link. So when we have this kind of structure, a natural question is to ask, what is the minimum number of spheres that we need to create a necklace representation? For example, here we have 3 necklace representation of the trefoil knot with different number of spheres. So we wonder what is the minimum number of spheres among all necklace representation for a given link.
Sorry, can you explain the rules how to build a necklace representation? So what are the conditions for these spheres? I see they intersect and
exactly. So the sphere can touch in the boundary, but they cannot intersect in the interior. So it's sphere packing. We can think about as a necklace of pearls of little spheres, but they are solid spheres. And in the interior of these spheres, we have like a rope, which is contained in the interior. This rope looks like thick, but actually it's just a curve. So we want a curve which is isotopically equivalent to the knot. I don't know if I answered the question.
So we just want that our knot would be inside.
Exactly, inside the sphere packing.
Mm-hmm.
So we can when we pass from one sphere to other sphere, we have to pass through the contact point. Is it clear?
Yes, thanks.
Okay. So, well, at the end of the talk, we will see that this question, which is purely a question in geometric knot theory, is going to be related with this question of number theory. Are there infinitely many integral solutions to this Diophantine equation? So let's put some terminology. What we want to study is this invariant, which is called the Ball number of a link. It's exactly the minimum number of spheres that we need to construct this necklace representation. This invariant was introduced by Mayara 20 years ago. For example, yeah, the Ball number of the trivial knot is just 3. We need 3 spheres to create a triangle. Mayara proved, for example, that the Ball number of the Hopf link, this link that we have here, is exactly 8. What does it mean? It means that we need 8 spheres to construct a sphere packing, where we can embed this link, and we cannot do it with less. And for example, this is the only link that we know today that we can actually compute the Ball number. For any other link or any other knot, we don't know the exact value of the Ball number. For the Ball number of the trefoil knot, for example, which is the simplest knot, Mayara and Oshiro proved that it's between 9 and 12. So they gave a construction with 12 spheres, and they proved that is it not possible to construct with 8 spheres. And they conjectured that actually the construction is optimal. So we cannot do it with less than 12, but it is still today an open question. So in some previous work, we gave a first algorithm for constructing necklace representations of every non-trivial, non-splittable link. Non-trivial means that we don't have trivial components, and non-splittable means that we cannot have components that we can put in different different bags, for example. And the proof is constructive. So it's an algorithm which takes a planar diagram of n crossings, and the output is a sphere packing. It contains 5 times the number of crossings. And inside this sphere packing, we have a net, which is it's called the contact graph. The vertices at the centers of the spheres we connect if our 2 spheres are tangent. Inside this graph, we can construct a closed loop, which is isotopically equivalent to the given knot or link. So this algorithm proves that the Ball number, the minimum number of crossings, is bounded from above by 5 times the crossing number, the minimum number of crossings. But actually, we think that this bound is not tight. We think that can be improved. Actually, we think that the exact value for any alternating link, alternating means that it would follow the knot. We alternate between upper and lower crossings, like this one. This link is alternating. For the class of alternating links, I think that the Ball number is actually 4 times the crossing number, that we need 4 spheres for each crossing. The conjecture, it makes sense because for making a crossing, we need 4 spheres. It's like a tetrahedron like that. And the question is how we can glue all these crossings to close in order to close and create a necklace representation of the whole link. And today we're going to see a method that we are going to do this construction for the class of links that are called rational links. And these are a class of links that are very closely connected with number theory. And the object that we're going to use for create this necklace representation are called Apollonian packings. So maybe you know, but for the people that don't know what is it, so an Apollonian packing of circles is an infinite sphere packing, or infinite circle packing actually, which start from this initial configuration of 4, we have 4 disks on the sphere, which are pairwise tangent. So we take 2 spheres and they are tangent. We project by using the stereographic projection, and we have this arrangement of 4 disks on the plane, in the compactified plane. When we project, we can have this effect that one disk has the interior outside because it contains the North Pole. Okay, and we have these empty spaces, which are actually curvilinear triangles made by 3 circles. In each curvilinear triangle, we can fill with exactly a unique disk of maximum radius. By doing this, we create new empty spaces. These empty spaces are again curvilinear triangles. So we can again fill it with new circles. And we can continue this process to infinity. And the limit case is called an Apollonian packing of circles. So it has infinitely many circles. And it fills the space now densely. So the complement of this construction is just has measure 0. This kind of objects, the Apollonian packing of circles has a lot of application in mathematics, in number theory, as we will see later, in number theory, in knot theory, and also in hyperbolic geometry. Also has been used in natural science, for example, for modeling in granular systems or molecular systems. The geometry behind this kind of objects use reflection groups. Actually, if we use reflection, we can construct infinite sphere packings. Sphere packings will contain infinitely many spheres. For example, here we combine 2 reflections and we produce an infinitely many spheres. If we can combine these reflections to try to fill the space in a better way, we can add more reflections like that. And if we use only reflections, we cannot continue to fill the space. We're going to use a different kind of reflection, which are called inversions, which are reflections through spherical mirrors. So instead of doing reflections through a plane, or a hyperplane, we're going to use reflections through a spherical mirror. So by adding this kind of reflections in the tool, now we can construct the sphere packings which are more dense in the sphere. And that's exactly what we use to construct an Apollonian packing of circles. We start from this initial configuration, and for each triple, we have a dual circle, which is orthogonal to 3 of these 4. It's the circle which pass through the contact points. There is a unique circle like that. If we apply now an inversion to the whole set, what happens is that the orthogonal circles are going to stay fixed. Since they are orthogonal, this part is going to exchange to this other part. And the same for this one and the same for this one. And the 4th disk is going to pass to this part. Now, if we combine with a second reflection, with a second dual inversion, we produce all the reflection that we can make. We make this infinite branch of circles. And we see that the space is going to be more filled. We add the 3rd dual inversion, and the 4th, we finished and we fill all the space. And that's how we can construct an Apollonian packing of circles. Is the union of the orbits of this action group made by the reflection of the dual mirrors acting on the initial set. If we start from a different initial set, for example, here we have a different initial set of 4 pairwise tangent disks. There are also a structure of dual mirrors, 4 dual mirrors. When we do the reflection, we construct a different Apollonian packing of circles. Now we want to generalize this kind of construction in other dimensions and with other combinatorics. And for doing this, we're going to use polytopes. And the polytopes that we're going to use are a class of polytopes which are called edge-scribable polytopes. So a D+1 polytope is called edge-scribed if every edge is tangent to the unit sphere. This polytope here is edge-scribed. Every edge touches the sphere in a single point. It's going to call edge-scribable if it admits a realization which is edge scribe. It's called canonical if it's edge scribe, and also verify the condition that the barycenter of all the tangency points is the origin. So some results about this kind of realizations. So Brightwell and Scheinerman proved that every 3 polytope is edge scribable. Every polyhedron admits an edge scribe realization. This is a very strong result, which actually implies other strong results like the Webe, Andreev and Thurston theorem on circle packet theorem. But this is not
sorry,
true.
but by realization you mean so that you have a polytope and then you can construct like a polytope which is like kind of has the same combinatorial
Exactly.
type.
Exactly.
But it's okay. So you don't care about like the edge length or whatever. You care
No.
just about the structure.
Just the phase lattice.
Okay.
So for every phase lattice which belongs to a 3 polytope, there is a realization, so a geometric embedding where all the edges are tangent to the unit sphere. And as I said, this is not true in higher dimensions. There are non-scribable polytopes in dimension 4 or higher. For example, the cyclic polytopes. I don't know if you know it. The cyclic polytopes with a lot of edges does not admit an edge scribe realization. And a good thing between edge scribe realization is the following. Every edge scribable polytope admits a canonical realization. So there is always a canonical realization. And this canonical realization is unique up to Euclidean isometries. So there is a unique canonical realization up to Euclidean isometries. That's why it's called canonical. So we can define, for example, the volume of this canonical realization is going to be an invariant of this edge scribable, or every edge scribable polytope. Another nice result is that every edge scribable realization is connected to the canonical one by a Mobius transformation. What does it? This implies that the realization of space of every higher of every edge scribable polytope, dimension 3 or higher, we look at the realization space, which are edge scribe realizations. So we put the condition that we want only edge scribe realizations. This realization space is just a point. So this is very counterintuitively, since in dimension 4 or higher, we have the universality theorem that says that the realization space of polytopes is very wide. But actually, for edge scribe realization, this realization space is just a point. They are all connected by a Mobius transformation. And that's exactly the object which is behind the sphere package that we're going to use. I'm going to make a connection between scribable polytopes and arrangement of spheres in the first step. So the recipe is just we take a polytope with the condition that every vertex is outside the sphere. Then we're going to put a light on each vertex. We're going to illuminate the sphere from each vertex, and we are going to consider these illuminated areas. Illuminated areas are disks on the sphere. They are spherical caps in higher dimensional sphere. Then we project with the stereographic projection. We obtain from each vertex, we obtain an arrangement of spheres and the Euclidean space, but we decrease the dimension. We start in dimension d+1 and we arrive in dimension d. No? Here, for example, we start with a 3 polytope and we obtain an arrangement of spheres in dimension 2. Okay, if we look at one edge, there is 2 interesting cases. If the edge is cutting transversely the sphere, then the illuminated areas of the vertices, they are going to be disjoint. In the second case, if the edge is avoiding the unit sphere, the illuminated areas, they are going to be overlapping. So in the middle case, if the edge is exactly tangent to the sphere, then the illuminated areas will be tangent. So if the polytope is edge scribed, which means that every edge is tangent to the sphere. Then here we obtain a sphere packing that we say that is polytopal. More generally, a sphere packing is polytopal if it comes from a edge scribe realization of a edge scribable polytope, and we can also apply a Möbius transformation. So it's up to Möbius transformation. Since all edge scribable realizations are connected with Möbius transformation, we can think about it's the canonical one. Some properties of these polytopal sphere packings is that the combinatorics of the polytope is going to be translated into the sphere packing. For example, the vertices of the polytope is the spheres. Okay, this is just by construction. The edges of the polytope encode the tangency relations between the spheres. So if there is an edge between two vertices, the two spheres are tangent. So actually, the graph of the polytope is exactly the contact graph of the sphere packing. And the question is, what are the facets? If we look at the facets of the polytope, they give us the dual mirrors that we looked before. So a facet is going to be the intersection of a facet with the unit sphere, going to give us a circle which is orthogonal to the sphere which corresponds to the vertices of the facet. And then we can use these dual mirrors to apply these reflections, and we construct an Apollonian packing in the case that we start from a tetrahedron. But we can use this construction for other polytopes, or any other scribable polytope. For example, if we start from a cube, we have the projection of the spheres. We take the dual mirrors, which are the intersection with the facets. We apply now the inversions, and we obtain a different Apollonian packing with a different combinatorics, which is carried by the cube. And it also works sometimes in higher dimensions. We start, for example, from a hypercube. We have the projection in 3D, it's a sphere packing in 3D, and we can do these inversions to produce an infinite sphere packing in dimension 3. So let's talk about now about the connection of these objects with number theory. Is there any question? Everything is clear? Okay.
I have a question about, you said that in the example that we have the number of faces equals the number of circles passing through points of where circles are tangent. So, and you showed 3 areas for polytope with 4 faces.
I cannot hear you very well. But...
you showed 3 circles for the in the previous slide.
Here?
Yeah, yes, here the here we have 4 faces, and can you show me the fourth circle? Like,
yeah, we have 4 faces. So here we have 4 dual mirrors. This is the question. The number of faces.
So we consider all possible ways to construct circle through these points. Yes, through points of touching.
Oh, I don't understand very well the question. So your question is how we construct the dual mirrors?
We build circles through all points where circles links. Okay,
Well, maybe
sorry.
No so just what maybe we should remind how this construction works, like again how.
Okay. So yeah. So for each vertex, we put a light which illuminates the sphere. We consider the illuminated area by this light that gives us spherical cap on the unit sphere. And then if the polytope is described, the illuminated areas, they're going to be tangent. And the tangency relations, the tangency structure is given by the polytope, is the skeleton of the polytope. And actually the facets of the polytope, the intersection with the unit sphere, is going to be a circle or a sphere in higher dimension, which is going to be orthogonal to these illuminated areas. Is the orthogonality that we need here. Sorry. This circle, which is orthogonal to these three, give us this circle, which is orthogonal. And this is the orthogonality that we used before to construct reflections, which give us the Apollonian packing.
So maybe the question was about like when you actually constructed these intersections with the circle, like so like there are three circles and there is the fourth one going around
Yeah,
those.
so
probably it was the
right.
question about this one, how you can visualize it on the picture. It's my guess what the question was. I don't know.
How we can visualize the fourth sphere here?
The fourth circle, like the
This
one.
Yeah. Okay, so we actually were going to project stereographically. So, so this circle, which is, if this is the North Pole, this circle is going to be the circle which is outside. When we project from here, this circle becomes this one, and the interior points are outside. This is how it works, the stereographic projection. And we have a circle which is behind a four facet, which is behind, but we cannot see it. It's in the south, let's say, and this is the circle that we found here when we do the projection. If there is another question, maybe we can see this later. For the others, it's fine. Can continue?
Yeah, sure.
Okay. So let's talk about the connection with number theory, which is a very nice connection and comes from a very old theorem, which was, we know that it was known before. The first track that we have is from Descartes, some letters that Descartes wrote to the Princess Elizabeth of Bohemia in the 17th century. And the result says that the curvatures, which are the inverse of the radii of four tangent disks, we have a configuration of four disks which are mutually tangent. If we look at the curvatures, they always satisfy this quadratic equation, no matter how we put the circles. I put here T3 because this configuration comes from a tetrahedron in dimension 3. Because we are going to generalize this later for other constructions. And the connection with number theory arises 300 years later, comes from Frederick Soddy in a paper of Nature. He noticed that actually if the four curvatures are integers, when we construct the Apollonian packing with all the circles, all the curvatures in this Apollonian packing will be integers. So let's start from this configuration. Here we have a configuration of four parallel tangent disks. So the radius here is 1/8, 1/8, and 1/5. And the radius of the big one is 1/3. And we put a minus because the interior is outside. We have this convention. Okay, so we have four curvatures which are integers. So they noticed that actually when we are going to fill the space, all the curvatures will be integers. And there is a many difficult questions which are open today about the behavior of these numbers here. They are closely connected with central problems in number theory, as the circle method given by Littlewood. Also, it's connected with the Riemann hypothesis. So it's very hard to understand the behavior of these numbers here. Here, for example, we have another configuration. We have four parallel tangent disks, which are the curvatures are integers. Then all the curvatures will be integers. There are generalization of the Descartes theorem for other polytopic sphere packings. And there is actually the most general version is due to Voigt, which use Lorentz geometry, but closed formulas for polytopic sphere packings were studied in particular cases. For example, for the simplicial case, so instead of a tetrahedron, for example, we can have a tetrahedron in dimension 4, then a similar formula applies. And we can also think about in higher dimension. So instead of a tetrahedron, we have a simplex in dimension d+1, and we have a configuration of d+2 spheres which are pairwise tangent. Then we have this formula, which is satisfied by the curvatures.
Can I ask another question? So
Yes, sure.
also about the Diophantine equations that are relevant to sphere packings, like whether freedoms in higher dimension, like, do you know like what sorts of Diophantine equations would make sense to like come up in sphere packings? You mentioned the circle method, so I was wondering if like the stuff you usually use to study using the circle method, like, does that often come from a sphere packing, or is that like something like very special? Or do you have any idea what families would make sense?
I mean, about the Diophantine equation, this is a very good question. I don't know which kind of Diophantine equation we can represent by this construction. For example, if we look at the Descartes theorem, they are going to be all homogeneous of degree 2. But we will see later how we can use it.
Okay, thank you. Yeah, thank you.
It's going to be in the next section. So for example, here, so before we talk about the generalization of sphere packings, which comes from simplices. We look at, for example, at the octahedron. We have an octahedron. We have a circle packing, which comes from the octahedron. Then there is also a closed formula for the Descartes theorem, given by Getter and Mallows. Also was given before, but Voigt with a different formulation. And this generalization was also given in a higher dimension, dimension 4, from Diaz and Nakamura. They gave a closed formula for the Descartes theorem for the curvatures of the spheres which come from a octahedron in dimension 4, which is called the orthoplex, or also the cross polytope in dimension 4. So the curvatures will satisfy this quadratic equation and also this linear relation between opposite vertices. There is also another formula for the cube given by Stange. And one of our results is we give a closed formula of the Descartes theorem for uniform polytopes for all the sphere packages which come from uniform polytopes. And the nice thing of this formula is that the coefficients of the quadratic equation are going to be expressed in terms of the geometry of the polytope. So we're going to very well understand what is going on with the polytopes and the quadratic equation. So for understanding these results, I'm going to talk about uniform polytopes. For talking about uniform polytopes, we need first regular polytopes. So the polytope is regular if its symmetric group acts transitively on its flags. Flags is just a sequence of faces which are contained one to the other. So, for example, in dimension 2, there is infinitely many regular polytopes, which are just the regular polygons. In dimension 3, we know it's very well known that there are only 5 regular 3 polytopes. These are the Platonic solids, the tetrahedron, the octahedron, the cube, the icosahedron, and the dodecahedron. In dimension 4 and above, there are only 6 regular polytopes. The simplex, which is the analog of the tetrahedron, the orthoplex, which is the analog of the octahedron, the hypercube, the analog of the cube, the 24 cell, which is the analog of the, no one of this one is the analog, it can be seen as the analog of the cube octahedron, which is not regular in dimension 3. The 600 cell, which is the analog of the icosahedron, and the 130 cell, which is the analog of the dodecahedron. In dimension 5 and above, there are only 3 regular polytopes: the family of the simplices, the cross polytopes, the orthoplex, and the hypercubes. So this is the complete list of regular polytopes in every dimension. So less regular families, the family of uniform polytopes. So a polytope is uniform if it's regular in dimension 2. in higher dimension, we are going to ask that all the facets are uniform. So it's a induction definition. Its symmetry groups act transitivity on its vertices. So every vertex is going to look the same, but we can have different types of edges. For example, we have the regular polytopes, the platonic solids are, of course, uniform in dimension 3. But also we have the family of prism and anti-prism, which are infinite. These are also uniform. So we see that the facets, the faces are regular. The vertices every vertex looks like the same. So the symmetry groups act transitively on the vertices. But we can have different type of edges. So this edge which connects a pentagon with a triangle is different from this edge which connects two triangles. We have also the family of Archimedean solids. So the faces are made by regular polygons. This is the complete list of uniform free polytopes in dimension 3. In dimension 4, there are also a list which is complete. And in dimension 5 and above, there is no complete list. It's an open question to classify all the uniform polytopes. So one thing that we are going to use for our Descartes theorem is this fact that any uniform polytope is exscribable, admits an exscribable realization. So hence it allows a canonical realization. And we're going to define the canonical length of this uniform polytope as the length of the half edge in the canonical realization. So we have the unit sphere, the canonical realization with all the tangency points. The barycenter is the origin, and we're going to look about this length. So this length is invariant. For example, the canonical length of the triangle is square root of 3. The canonical length of the tetrahedron is square root of 2. This is one definition that we need. And the other definition is called the polytopal curvature of a polytopal sphere packing. So instead of define the curvature also only for disk, which corresponds to vertices, we're going to also define the curvature of any kind of face. So we're going to define the curvature of a face with respect to a face of the polytope as the arithmetic mean of the curvatures which correspond to the vertices of this face. For example, here we have tetrahedron, we have the sphere packing, which corresponds to the tetrahedron. Every circle corresponds to a vertex. If we look at one face, for example, the face given by the vertices 1, 2, and 3, this triangle, the polytopal curvature of this triangle is going to be the arithmetic mean of the curvature of the vertices. So we have 3 circles here. We take the arithmetic mean, and this is going to be the polytopal curvature with respect to this face. And we can do this for every face. Okay, so these are the only 2 definitions that we need for the Descartes theorem that we're going to give. So our formula is for every polytopal sphere packing, a sphere packing which comes from a polytope. If the polytope is uniform in no matter the dimension, then if we take a flag of this polytope, a sequence which starts from a vertex, an edge, and we continue to the polytope, and we have that the polytopal curvatures of the faces that we have here, they are going to satisfy this quadratic equation. And the next thing is that the coefficients in this quadratic equation are determined by the canonical lengths of the faces that we have here. Let's do an example. If we start from the tetrahedron, we take a flag. For example, this flag start from the vertex 1, then the edge 1, 2, then with the face 1, 2, 3, and the whole polytope. So we need the canonical length of the faces that we find in this flag. So we have a triangle. The canonical length was square root of 3, and the tetrahedron canonical length is square root of 2. When we plug this into the formula, we find this quadratic equation. If we replace with the formula of the definition of polytopal curvatures, we found again the classic Descartes theorem. If we do this for every dimension from the simplex, we have a formula for the canonical length that we plug into this formula, and we find the generalization of the Descartes theorem for every dimension. We can do this also for the octahedron, different values here, different formula, and we find the Descartes theorem for the octahedron. The octahedron in every dimension also. We find a formula, a nice formula for the octahedron in every dimension. For the cube also, it works. And it works for every uniform polytope, in particular for the family of cubes in every dimension. So now we have a connection, we can understand the coefficients of this quadratic equation. So if we combine this formula with the combinatorics of the polytopes, we can construct packing integral packings with all the curvatures are integers. If we can do this, then we're going to say that the polytope is packing integral. For example, it is well known that the octahedron and the cube are also packing integral. But for example, the dodecahedron and the icosahedron and the decahedron are not packing integral. So the curvatures we can not realize as integers, but they can belong to the number field Z phi, where phi is the golden ratio. But if we only look at which polytopes are packing integral, what we want only integers. For example, Child-Roth, Cui, and Stier give the complete list of, there are only 8 uniform 3 polytopes, which are packing integral. We can construct this family of integers. These are made by the tetrahedron, octahedron, cube, the 3 prism, the truncated tetrahedron, we truncate the vertices, the truncated octahedron, the cube octahedron, and the 6 prism. There is only 8. The others are not packing integral. So this is an open question, which 3 polytopes are packing integral? So we now use this formula for the Descartes theorem. We can manipulate to construct other formulas or Diophantine equation that if we use now the integrality of the curvatures, we can construct solutions to this Diophantine equation. So imagine that we want to solve this quadratic equation, or we want to find solutions, integral solutions. And this formula comes from this Descartes theorem for the cube. These M are just the sum of these curvatures. And the curvatures that we need here is a sequence of vertices where we start from a vertex and we end by this antipode. We create a path of curvatures. And these are the curvatures that we plug here. For example, this is the one path given like that. And this Descartes theorem gives us the solution. If the curvatures are integers, then we take, for example, the difference of these two, give us the 5, the difference of the 2 gives us the 3, the difference gives us the 4, and the sum of the last two give us the 4th solution. So if we change a path in a different integer configuration, we obtain a different quadratic equation, a different solution. Again, another path gives us another solution. So this is the question that someone asked before. Which kind of Diophantine equation can be solved with this kind of methods? So can we, in other way, we start from a quadratic equation with some coefficients. Can we find a polytope which is packing integral which solves this equation? So a different thing, which is not related with Diophantine equation, is more to study the structure that we can find between the numbers here. It's going to be given by taking sections. So polytopes are combinatoric objects, but they are also geometric objects. And we realize these objects in Euclidean space. And we can do geometric operation like taking a section with an intersection with a hyperplane. So a section of a polytope with a hyperplane gives us another polytope of a smaller dimension. If we do the same for a polytopal sphere packing, we take a section, and sometimes it turns out that the section gives us another polytopal sphere packing with a smaller dimension. And to study these things, which kind of polytopes we can find when we do this operation, we have introduced the notion of Apollonian section, which is just, okay, the packing is given by the action of a group acting on a set. So we're going to take a subgroup and a subset. And we're going to study this kind of group. So we're going to study the subgroups that we can construct here. So with this section, with this notion of a polynomial section, we prove that, for example, every orthoplex, so the octahedron in dimension 4, contains a section which corresponds to a tetrahedron, an octahedron, and a cube. For example, if I start from the orthoplex in dimension 4 and we construct the polynomial packing, we can find a section which corresponds to the octahedron. We can do the same for the tetrahedron. For example, we can transform this configuration with a Mobius transformation. We can apply the Apollonian construction, and the section here give us a sphere packing which is in bijection with the classical one, with the construction given by the tetrahedron. We can do the same with the cube. We can transform this with a Mobius transformation. So these 8 spheres becomes these 8 spheres. We apply the polynomial construction, and intersection with this middle plane give us a circle packing which corresponds to the construction given by the cube. This section, the cube, is a bit special because the section that we take here is not a cross section. So the circles have not cut it in the middle. So the centers of the spheres are not in the plane. And we can see that the combinatorics here of the spheres and the disk are different. In the previous sections, for example, here in the tetrahedron, if 2 spheres are tangent here, then the spheres are going to be tangent here. So we have the same combinatorics. It's not the case for the cube. Here we can find 2 spheres which are tangent in dimension 3, but the disk here are not tangent in the project in the section. This can be used to understand the connection between the numbers that we can find, for example, in the packings of the tetrahedron or octahedron or cube. For example, for the cube, these numbers can be found in an integral construction given by the orthoplex. So when we took the section, we find exactly the same numbers. So we can study the connection, if this class of numbers are contained into this one, and maybe some problems which are open for some polytopes, we can solve it in another polytopes. So this is the part which is related with number theory, but actually this object that we used for number theory is exactly the nice object. The section of this cross polytope, which is in correspondence to the cube, is exactly the object that we need to construct knots. And that's the last part of the talk. So we're going to come back to the part of geometric knot theory. These kind of objects are very useful for constructing knots. For example, if we start from a knot, when we add spheres, we can wonder if there is a path in these spheres, which give us a necklace representation of this given knot or link. And actually, we prove that it's true that for every link, we can continue adding spheres here to construct a necklace representation of the given link. And this is going to work for the tetrahedron, for the octahedron, and the cube in dimension 4. So these constructions are complex enough to contain every knot or link. And we wonder if this necklace representation can be optimal in the sense that maybe we can use very few spheres, and maybe we can improve the upper bound that we had before. This is the upper bound that we had before. So we have an algorithm. We start from a diagram and give us a sphere packing with 5 times the number of crossings. And in this sphere packing, we can find a necklace representation. When it turns out that if the link is rational, we will see what is rational. And then we can use the Apollonian packing given by the orthoplex, the octahedron in dimension 4. So instead of using 5 per crossing, we're going to use only 4 spheres per crossing. So this construction is going to be more optimal. And this is the result that for every rational link, the ball number, the minimal number of spheres is going to be bound above by, instead of 5, now it's going to be bounded by 4 times the number of minimal crossings. I'm going to explain this result because this is the result which connects sphere packings, Apollonian sphere packings, knots, and number theory. Because rational links are very closely related with number theory. What is a rational link? So a rational link starts from a link like that, an arbitrary link. We consider the intersection of this link with a sphere which is called the factorization sphere. And we look at what we have inside. So inside we can have a collection of paths where the endpoints are in the boundary, and we can also have in the interior we can have closed loops, and this is called a tangle. When we have a tangle, we can modify this tangle by doing geometric operations. For example, this we can apply a reflection on this plane which pass through this in the opposite endpoints. When we do this reflection, we modify the tangle. This operation is called a flip. And we can also apply another operation which is called the half twist. We take the endpoints on the each side and we're going to add a crossing. And we can add positively or negatively. So we have a positive half twist and a negative half twist. And then because we are in topology, we can push this structure inside and we have a different angle. And we have these 2 different operations. With these 2 different operations, Conway defined an algorithm which is called the Conway algorithm, which starts from this initial tangle, and we are going to iterate flips and half twists. The number of half twists that we're going to apply in each iteration is encoded by a sequence of integers. So let's do an example. If we start from the sequence 2 minus 2 minus 3, these are the operations that we're going to apply. We start from this initial tangle. So first of all, we flip. So we do the reflection. And we are going to add 3 half twists in the negative way. So we add 3 crossings. And we flip again. We add 2 negative crossings. We flip again, and we add 2 positive crossings. And this construction is called a rational tangle. So what is a rational link? It's just if we close the endpoints with 2 arcs from outside, we construct again a link. This is called a rational link. And why they are called rational? Because actually they are in bijection. Rational tangles are in bijection with rational numbers. In this bijection, a rational tangle is going to correspond to a rational number. The flips, they correspond to take the multiplicative inverse. And the half twist corresponds to adding plus or minus 1. So when we apply the Conway's algorithm, the initial tangle is just, we start from the infinity. And for example, if we start from this sequence, we're going to do the same operation, but now with these new definitions. We start from the infinity, we flip, so we take the multiplicative inverse, 0, by definition. Then we add minus 3, and we flip, so we take the inverse. Then we add minus 2, and we take the inverse, and we add plus 2. And what we get a continued fraction, where the numbers are given by the sequence. So this continued fraction evaluates into a rational number. And this rational number, Conway proved that it classifies the tangle under isotopy. So for example, if we start from 2 different sequences and we construct 2 different tangles, rational tangles, if the continued fraction evaluates to the same rational number, then we can pass from one tangle to the other continuously without cutting the arcs. So these rational tangles are encoded by a rational number. So that gives us a connection between rational links and rational numbers. Not every link is rational, but for the rational links, there is a very good structure behind, given by the rational numbers. And that's exactly what we're going to construct in our construction with polytopal sphere packings. So we have this section, which is the section of a polytopal sphere packing given by an orthoplex, octahedron in dimension 4. We take a section which corresponds to the cube. And in this section, we can look there are two types of sphere. There are spheres which are above this plane, and there are spheres which are below this plane. We have infinite spheres, and these 4 spheres is exactly that we're gonna use to make a crossing. And this bunch of infinite tetrahedrons we can find here, they are gonna be placed in a nice way that we are gonna glue all together to construct the link. So the thing is the key is that we are gonna copy the Conway's algorithm for this structure. So we're gonna look only at the spheres which are tangent to this plane. So we don't look at all the spheres. We only need the spheres which touch this plane. And this sphere, the set of this sphere, we call it the orthocubic packing. So it is the Apollonian packing given by the orthoplex, but corresponds to the cubic section. So it's the orthocubic packing. We're going to construct rational links inside this sphere packing. So we're going to copy the same algorithm. Instead of taking a factorizing sphere, the discrete version is going to take a factorizing tetrahedron. So we're going to look at only the paths that we can create here. So we have here infinite spheres, and we're going to look at paths which connect to the 4th corners. So we're going to define an orthocubic tangle, which is just 2 disjoint paths, which goes from one corner to the other, and it goes through these infinite spheres. So this is an orthocubic tangle. So it's a discrete version of the classical topological tangle. So let's copy exactly the same. So instead of a topological tangle, we have an orthocubic tangle. We want to copy the flip operation. Well, this is easy. It's just taking the reflection on this plane. The reflection belongs to the symmetry group of the whole configuration. And they're going to change the tangle, the orthocubic tangle here. And we can also do a half twist by doing Mobius transformations. We can do an inversion, which push all the structure into this structure here, because there is a fractal structure. So every copy that we can find is exactly the same. The structure is repeating until infinity. So this structure can be pushed here, and then we can add a positive crossing. And also we can add a negative crossing. So with these 2 operations, we can define then a Conway algorithm with this new flip and this new half twist. We're going to start from this initial tangle, which corresponds to the initial tangle that was in the topological version. So we have 4 spheres, and we take these 2 paths. And we're going to do flips and half twists with these new definitions. For example, for the sequence 2 and 2, let's see what happens. So we make a flip. So we change this construction by doing a reflection. Then we apply a half twist. So these 4 spheres becomes here. And then we add a positive crossing. Again, in the end, we have this new orthocubic tangle. We can repeat this by doing another half twist. So this structure is pushed here, and we add a positive crossing. And we have this new tangle. And we flip the whole construction. And then we add a positive crossing and a second positive crossing. And at the end, what we obtain is a geometric construction of the rational tangle 5/2. The 5/2 which corresponds to the continuous fraction given by 2 and 2. The nice thing is that we can always close this tangle without adding new spheres. And by closing the tangle, we construct a necklace representation of the rational link, which is given by the closure of the tangle. And we can do this for every sequence. So this proves that every rational link is contained in this orthocubic packing. So we can wonder if maybe we are using the minimum number of spheres. Maybe this construction is optimal. But actually, if we count the number of spheres, it's not optimal. We use 5 times the number of the crossings. But the good news is that we can modify this Conway algorithm by, instead of starting with this tangle without crossing, we can start with a tangle with already one crossing. If I'm using this modification of the Conway algorithm, now, yes, we are going to add 4 crossings, 4 spheres per crossing. So we have a crossing here, and each time that we add a crossing, we add only 4 spheres. And at the end, we can close. And in this way, we can construct a necklace representation of every rational link with 4 times the number of minimal crossings. This is the proof that for every rational link, the bold number is bounded by above by 4 times the number of crossings. And here is the connection with number theory. The nice thing is, if we look at the classic construction given by the Conway algorithm with this kind of spheres, the nice thing is here in this construction we can find the fraction which corresponds to the tangle. For doing this, we're going to project the construction that we have in 3D into the plane. And we have this construction. And we are going to look at this specific point that we find here. This is the point of the tangency of the last 2 spheres in this construction. Well, the surprising thing is that the coordinates of this point reveals the fraction which corresponds to the tangle. Actually, we can prove that this point is the intersection of this circle with the line where the slope is the inverse of the square of the fraction. And this works for every fraction. So this can be seen as a geometric interpretation of the correspondence between rational tangle, which are topological objects, and rational numbers. For proving this, we can prove it analytically by computing the coordinates, the Cartesian coordinates, but there is a nicer way to do it. We can use the Lorentz geometry. And this is given by the Lorentz space. So the Lorentz space of dimension of D1, dimension D is the vector space of dimension D plus 1 with an inner product given by this inner product. It's a pseudo inner product where it's like the classical one, but the last coordinates we put a -1. So the signature of this inner product is D1. When we have this inner product, we can also think about, we can have vectors with have normal pseudo norm equal to 1. This is the unit sphere with this new inner product. We can have vectors with norm equal to 0, which are not 0. And we can have also vectors with norm equal negative norm. This is the picture of in dimension 2 of the Lorentz space in dimension 2. The Lorentz space in dimension 3 is the same, but we make a revolution. So for example, the unit sphere, which means the vector with Lorentzian norm equal to 1, is now this hyperboloid. And the vectors which has norm 0, Lorentzian norm 0, are a cone, which is also called a light cone. The connection with the spheres is that in the Lorentz space of dimension D plus 2 corresponds to spheres in dimension D. This is, and we can see the connection very quickly. It's not very difficult to see this connection. So we start from a sphere in dimension D, and when we apply the stratigraphic projection, as we see here, we have a spherical cap on the sphere, and this spherical cap corresponds to a light source, as we did before with the polytope. So this sphere corresponds to a point in dimension D plus 1, which this point is outside the sphere. So we put all this frame in dimension d+2 in the hyperplane of length of heightness 1. This point corresponds to a vector that we can normalize to get a vector belonging to the unit sphere of the Lorentz space in dimension d+2. So every sphere corresponds to a unit vector in the Lorentz space of dimension d+2. So every sphere, we can encode it with a vector, for example, in dimension 2, we can encode it with a Lorentz vector in dimension 4 with the Lorentz norm is equal to 1. We change the sphere, we change the Lorentz vector, but always the norm is equal to 1. And it works for every sphere. Spheres corresponds to unit vectors, but in the limit case, if we take the radii goes to 0, then we get a point. Then we have that the vector becomes a direction in the light cone. So points in this connection corresponds to directions in the light cones. So we can encode a point, for example, in R2, with a Lorentz vector in dimension 4, but this time the Euclidean norm is equal to 0. The Lorentzian norm is equal to 0. So we change the point, we change the Lorentz vector, but the Lorentz norm now is equal to 0. And that's that we use here. We're gonna compute the coordinates of the Lorentz vector of this point. And we prove that for every P and Q, for every fraction, the coordinates of the Lorentz vector are those one. Since it's a point, this vector, the Lorentz vector, has a Lorentz norm equal to 0, which implies if we do the Lorentz product here is equal to 0, so we have this equation here for every fraction. But this equation parameterized this Diophantine equation, the Diophantine equation that we saw at the beginning. So the same method we construct necklace representations, optimal necklace representation for rational links, give us solutions, primitive solutions for this quadratic equation. And this is how we connect rational links with number theory using polytopes and sphere packets. We change the rational link, we change the solution. So these are the references which you can find the methods for the Apollonian packings and knots. And that's everything. Thank you very much for your attention.
Yeah, thank you very much. So are there any questions?
Here's a question. So at the very beginning, I mean, I guess usually you look at these like upper bounds for the ball numbers. And you said these bounds might not be sharp. Is there anything you can say about like interesting things about the lower, like non-trivial lower bounds?
Yeah, this is a very good question. There are no good methods for lower bounds.
Okay.
That would be very nice if someone finds a. There are for instance, I think there is a nice clue is to understand the lower bound of the trefoil knot and try to generalize for the other knots. I'm gonna change the screen just. Okay. Yes. But yeah, there are not good methods for lower bounds. That would be interesting to find. I don't know if I answered your question.
I guess it's what's the current situation. So.
Okay, any other questions?
I guess like the big question is like what makes it like so hard to find a lower bound really, but I guess yeah, I can just try looking at this.
I didn't understand.
I guess the question was really like what makes it so difficult to like find like
what makes difficult? Yeah. Sorry. Yeah, for upper bounds, you need just to construct you need to give a nice construction, no?
Right.
For lower bounds, you need to prove that in every configuration,
Right.
no matter the size of spheres, you
Yes.
cannot, so there is a local restriction. And that's
Right.
the difficult, like to understand
Okay.
the space of all the necklace representation, which is very wide.
Yeah, I guess so.
So for the lower bound of the trefoil knot, there was like a trigonometric abstraction that my area used. But this is because with the trefoil knot, there are all very few spheres, so you can check every case.
Right.
To give a general lower bound, I think it's much more difficult.
All right.
I see. So there's kind of proof, but like no understanding of like the nature.
Yeah, exactly.
Yes,
So it's like
I
very
see.
specific to that particular.
Yeah,
I see.
exactly.
I guess if there are no other questions, I will turn off the recording.